Okay, hello everyone. In this lecture series, we are discussing variational principle and corresponding questions. Last class, we have been discussed this question: evaluation of ground state energy of linear harmonic oscillator having mass m and angular frequency omega. In detail, we have been discussed. Okay, by considering these steps or procedure. In this class, we are going to discuss another new type of question. That means we have to find out the eigenvalue of fast excited state of 1D linear harmonic oscillator. Here in the question, it is written that estimate the upper limit or the approximate value of fast excited state eigenvalue. Okay, approximate value or eigenvalue for fast excited state of 1D harmonic oscillator. Here trial wave function has not been given. So how we are going to solve this question, that we are going to discuss in this video. Okay, so let us start. So here in the question there is no trial wave function given. First we have to construct the trial wave function. Previously we have been estimated the ground state energy of a linear harmonic oscillator by using trial wave function, this one, c e to the minus ax square. Okay, and c is your normalization constant, and we found after normalization the value was 2a by pi to the power 1 by 4. You can refer the previous video. Okay, this question already we have been discussed, and here a is the parameter. For 1D harmonic linear harmonic oscillator, the Hamiltonian always this one, minus h cot square by 2m d square, here d square by dx square plus 1 by 2 m omega square x square. Okay, now we have to construct the trial wave function for this question. Here heading I written construction of trial wave function for fast excited state. We know this is the probability, wave function of ground state of a linear harmonic oscillator, and this is your wave function for fast excited state. So it has one node here. For the ground state there is no node, and also we can found the probability also, or wave function also we can found beyond the classical limit. So this is the classical limit. Beyond the classical limit also we can found the wave function. So obviously we can found the probability beyond the classical limit, whatever we know in our plus 3 level. Now the wave function here for trial wave function for fast excited state, these conditions should be satisfied. That means the wave function must be odd. It must have one node at x equal 0. Psi x should be 0 at x equal to plus or minus infinite. Okay, so what will be the trial wave function? So this is the trial wave function for ground state. So for the ground state at plus or minus infinite, it should be 0. Here if I am going to put instead of x equal to minus infinite or plus infinite, the psi will be 0, which is represented by this figure. But in case of fast excited state, these 2 points also we have to consider. That means it should be a odd function and it should have a one node itself. So here if it is so, then the trial wave function will be in the form of like this: psi 1 x will be equal to b some normalization constant x into e to the minus a x square. Here if I am going to put x equal to 0, then psi 1 x equal to 0, that means one node we can found here. Okay, and at x equal to plus or minus infinite, if I am going to put plus or minus infinite, so we can found e to the minus infinite, so psi 1 x will be 0. So this equation number 2 represents the trial wave function of fast excited state of a 1D linear harmonic oscillator. So as it is not normalized, b is the normalization constant, we have to use the normalization condition, and we can estimate the value of b. So here b value we can found 32a cube by pi to the power whole to the power 1 by 4. Here I am not going to discuss all the steps. It is very easy. You can follow the note. Okay. Here normalization constant b we found 32a cube by pi to the power 1 by 4. Let this is your equation number 3. Here psi x and psi 1x are orthogonal with each other. That means the psi 0x ground state wave function and fast excited wave function should be 0. That means this condition should be satisfied. You can check by yourself. This will be 0. That means if I am going to consider here c value is your this one 2a by pi to the power 1 by 4, and b value is your 32 by pi a cube to the power 1 by 4 e to the power minus a x square, x e to the minus x square. You can do by yourself in your rough. You can found the value will be 0. Okay, so these two steps no need to write in your exam. Here we found the normalization constants. Therefore, the normalization wave function for fast excited state will be 32 into aq by pi to the power here aq to the power 1 by 4. Mistakenly, I written 1 by 2. This is 1 by 4. Okay, into x e to the power minus a x square. Let this is your equation number 4. Okay, now we have to go for the second step, that is your expectation, finding the expectation value here. Sorry, third step. Here we retain the Hamiltonian of this system. The system Hamiltonian is this one, represented by equation number 1, and we found the normalized wave function is this one. Normalized wave function is your this one, represented by equation number 4. Now we are going to go for the third step, that is the calculation of expectation value of Hamiltonian. So by considering the normalized wave function, expectation value of expectation value of Hamiltonian for the state psi 1 will be equal to minus infinity to plus infinity psi 1 star h cap psi 1 dx by minus infinity to plus infinity psi 1 star psi 1 dx. But this value will be equal to 1 because psi 1 is your normalized wave function, no need to write. Now we are going to calculate this integration, minus infinity to plus infinity, this one, psi 1 star h cap psi 1 dx. So here psi 1 star will be how much? This one, 32 aq pi to the power 1 by 4 into x e to the minus ax square, and psi 1 also same. So this is the constant. If we will multiply it with again with this same value, then it will be 32 aq pi to the power 1 by 2 taken outside of this integration, minus infinity to plus infinity, x e to the power minus a x square written as such, and Hamiltonian is nothing but minus h cos square by 2m d square by dx square plus half m omega square x square. Again we have to write the same term, x e to the power minus a x square dx. Okay, now 32 aq by pi to the power 1 by 2 written as such here, x e to the power a x square. Here I segregated the two parts. One is your kinetic energy part, one is your potential energy part. That we know, this is your kinetic energy and this is your potential energy part. So separated by two terms, minus h cot square by 2m d square by dx square here, operated over x e to the power minus ax square dx, and potential energy part if I'm going to consider here 1 by 2 m omega square, 1 by 2 m omega square, x square is there here, 1x here, 1x will be x to the power x square. See, this x square, x into x, again x square, so x to the power 4 we can get, e to the power minus ax square, e to the minus ax square, so it will be e to the power minus 2x square. Mistakenly written over here, e to the minus 2x square. Okay, now in the next step what we have to write, same this term written as such, minus infinity to plus infinity, x e to the power minus ax square here, minus h cot square by 2m minus h cot square by 2m, double derivative of this one, x e to the power minus ax square will be this much, minus 6a plus 4ax square x square 4a square x square into x e to the power minus a x square. This much value you can found the double derivative of this one, x e to the minus a x square. You just try in your rough. Here I'm not going to solve this one, you just do by yourself. Okay, and next term is this much written as such here, half m omega square taken outside of this integration, minus infinity to plus infinity, x to the power 4 here, e to the power minus 2x square dx. Okay, now the constant term written as such here, minus here I'm going to multiply this, minus h cot square by 2m minus 6a minus h cot square by 2m 4a square x square with this term also. So here we can get the two terms by multiplying this this term with this one and this one. Okay, here minus h cot square by 2m minus 6a, so it will be plus h cot square by 2m 6a minus infinity to plus infinity integration, here x is there, here x e to the power minus ax square, here x e to the minus a x square. So it will be x to the power 2 x to the power 2 e to the power minus 2a x square dx. Okay, next term will be minus h cot square by 2m into this much minus h cot square by 2m. Here 4a square is there, 4a square. Here you can see x square x cube, here x to the power 4 x to the power 4, here e to the power minus a x square, here e to the power minus a x square. So it will be e to the power minus 2 a x square dx. Got it? Now last term written as such minus plus 1 by 2 m omega square, this one minus infinity to plus infinity. Okay, x to the power 4 e to the power here e to the power minus 2a x square dx. Okay, okay, now we are going to go for our next step. Next step I not written here, I am going to write carefully, you have to watch. This 32 a cube by pi to the power 1 by 2 can be written in this way. Here 32 to the power 1 by 2 is nothing but 4 root 2 a to the power 3 by 2 by root pi. Okay, okay, then your this first term will be, you just write, okay, you just write h cot square by 2m 6a. Here this integral is a even function, so it can be written as 2 into 0 to infinite x square e to the power minus 2a x square dx, because we can apply the gamma function on this integration. Okay, minus h cot square by 2m is there, you just write into 4 a square into, again this is also even function, also we have to write 2 into 0 to infinite x to the power 4 into e to the power minus 2a x square into dx. Now last integration is your this one plus, here this is also even function. If I am going to write 2 into 0 to infinity, then it will be 2 will be got cancel, m omega square 0 to infinite x to the power 4 into e to the power minus 2a x square dx. Okay, okay, now I am going to write the next step, carefully you have to watch. This is your 4 root 2 a to the power 3 by 2 by root pi. Uh, this will be just to write, okay, h cot square by 2m 6a into 2. Okay, what will be this value? This value, see, if we have this type of integration x to the power n into e to the minus x to the power m into dx, already we know this is the gamma function. This value is your 1 by m into 1 by a to the power n plus 1 by m into gamma n plus 1 by m. You just compare this integration with this integration. So here m is nothing but your 2 and a is your 2a and n is your 2. So what will be the answer here? 1 by m, nothing but 1 by 2 into 1 by a means 1 by 2a to the power n plus 1 by 2. N means 2. 2 plus 1 means 3. 3 by 2 gamma m plus 1 by n plus 1 by m, that means also 3 by 2. Okay. Next, here this integration we have to consider. First we have to write the coefficients. H cot square by 2m. Here this will be 4a square. Just this is your rough work that you have to do. And this integration also can be solved by using gamma function. How much it will be? 1 by m means 1 by 2 into 1 by a to the power. Here a means 2a. 2a to the power n. N means 4. Here n means 4. 4 plus 1 5. 5 by m. 5 by 2 into gamma 5 by 2. Okay, okay, then last integral, this is your m omega square. See, this integral, this one and this one is same, so what we have to write? Directly I have to write 1 by 2 into 1 by 2a to the power 5 by 2 into gamma 5 by 2. Now you have to solve these things by yourself in your rough, okay, and you can found the value expectation value of Hamiltonian will be equal to, you just carefully have to solve. Okay, expectation value of Hamiltonian, you can found how much? 3 h cot square a by 2m, 3 h cot square a by 2m, okay, plus 3m omega square by 8a. This will be your expectation value of Hamiltonian for the state psi 1. This one. Okay. Okay. Now we have to minimize this expectation value of Hamiltonian at the state psi 1, considering the parameter as your a. So what will be the condition? Condition is your differentiation of expectation value of Hamiltonian with respect to a will be equal to 0. That means this value will be differentiated with respect to a and equate to 0. Same thing I have been done over here. You just put the heading minimization of expectation of Hamiltonian for the state psi 1. That means differentiation this value with respect to a. The first term will be how much? 3 h cot square by 2m. Okay, 3 h cot square by 2m is the constant, a is there, so 3 h cot square by 2m. And the second term, if I am going to differentiate with respect to a, it will be 3m omega square by 8 is the constant, 1 by a will be minus 1 by a square, minus 1 by a square. So it will be minus 3m omega square by 8a square equal to 0. Okay, just to simplify, you can found a value is your m omega by 2h cot. Okay, you just put it this one in the red bracket, red box. This is your final output of the Hamiltonian. Now we have to substitute this a value. This is our last step. Now we have to substitute this a value in this Hamiltonian. So instead of a, we have to put m omega by 2h cot. 3 h cot square by 2m is there. 3 h cot square by 2m. Instead of a, what we have to put? M omega by 2h cot. Here m omega by 2h cot. Here a, instead of a, we have to put m omega by 2h cot. So it will be 2h cot by m omega. So you just solve it. This one represents what? The energy eigenvalue of first excited state. So you just write, therefore the energy eigenvalue of first excited state, energy eigenvalue approximate, okay, approximate energy eigenvalue of first excited state will be this one, this value. You just simplify it, you can found 3 by 2 h cot omega. Okay, already we know this value. In general, for a linear harmonic oscillator, we know this value 1 n plus 1 by 2 h cot omega. N is your 0, 1, 2 like this. For ground state, n equal to 0, so half h cot omega already we found in our previous question. You can check that video. For first excited state, n will be 1, so 1 plus 1 by 2 will be nothing but 3 by 2 h cot omega. So here we found the same exact value of fast excited states eigenvalue by using variational principle, 3 by 2 h cot omega. Now the wave function, normalized wave function, the normalized wave function of fast excited state will be what? Already normalized wave function we found here. This is the representation of normalized wave function. Equation number 4. Here instead of a, we have to put the a value here also. So 32, you just put and simplify, you can get this value. Okay, so here I am going to stop this today's class. Next class we are going to discuss finding the ground state energy of helium atom. Ground state energy of helium atom by variational method, by using variational method. So thank you so much for watching this video. Thank you.